Okay, so let's get started. So the final topic today is Allison Moore, and she's going to tell us about Tangle decompositions and the immersed curve.
Thank you. Thanks, Ken, for inviting me. This has been really interesting, and I'm glad to be around all of you all. Let me draw a Tangle decomposition on the board. I'm going to say a few things that everybody here knows for a little while, but for a Tangle decomposition, I want to take a knot in S3, and let me write that knot like this: Tangle 1, union Tangle 2, union over a sphere. And by tangle Ti, I really mean a pair. It's a 3 ball and 2 properly embedded arcs. So I'm just considering these kinds of tangles. You can, consider more general kinds of tangles, or you could consider tangles with closed components, but I'm not going to do that. So I have a picture to go along with this. T1, T2, and I'm going to kind of do my numerator closure in this kind of flight way, so that it matches up with the technology being used later. So I could flight this over, and I'd have the second tangle flipped over, and that would look like your typical numerator closure of T1 plus T2, rotated T2, so tau T2 or something like that. Okay. So let's also recall Conway spheres. Okay, so Conway sphere. S is an embedded 4-function sphere. So that's this S that I have right here. This S isotopic to that S. And S is essential, an essential Conway sphere. If S minus those 4 points is a compressible in the complement of the knot. Okay. Or pi 1 effective. Okay. So let me state a theorem, and then I'll try to motivate it and replace it with a different statement. So here's the theorem. Here's a theorem, and this is all sort of going to be an advertisement for proof technique, I guess. So I'm going to abbreviate everybody's names because there's just many consonants. Okay, so let's let T be a tangle. Let's let T be a tangle with an unknot closure, or a closure to an unknot. To an unknot. Then if T closed off with some rational tangle QR, so there's this rational closure, is isotopic to this different rational closure, QR prime, with this type of tangle decomposition, and either the tangle that we started with was a rational tangle, or the parameters R and R prime were the same, so R is equal to R prime. Okay, so the slope of the rational tangle. Okay, so just as far as language goes, like I get sloppy and I call it an unknot closure, but I mean this T has some sort of other tangle closure that gives you an unknot, whereas this is a rational closure in the sense that I'm plugging in a rational tangle and getting some knot.
So the closure of the unknot doesn't have to be a rational.
No, it could be any closure. It could be like some other tangle. Yeah, I should an unknot closure, meaning like T plus T prime, or T union T prime is an unknot. And these are the rational tangles in the sense that, like, so QR is going to be a tangle that I can write kind of with this type of thing, where I have the continued fraction expansion of the rational number, giving me the description of what this tangle looks like. This is maybe some non-standard notation, but p over q, or infinity. So let me point out that if t is rational, there are kind of silly cosmetic tangle fillings. So just as a brief little example here, if t is rational, then you can have examples like this. So let me just take the rational tangle 1. Maybe that's -1. I guess that's -1. It doesn't matter, but let me close it in this way. Okay, I get an unknot. I'm flagging my picture, not doing that closure, but so this is some t plus q infinity, union. I'm gonna forever scribble my notation here. Or I could close it in this way. This should also, as long as I got my crossings the right way, this is probably also an unknot. It shouldn't be a trefoil, it should be an unknot. So, you know, this has an unknot closure. This is an unknot. This slope is infinity, and this slope is 1/2. Or this is maybe, no, this is 0, and this is 1 or 2, but they're different r's. Okay, so r is not r prime here. Okay, so
how restrictive is the closure to an unknown?
how restrictive?
Yeah, on T.
It's pretty restrictive, I guess. Well, I mean,
You mean in the sense of like how many tangles?
Yeah, I mean,
have
if somebody
closure
throws a generic tangle out at you.
I would say generic tangles.
no, probably don't. Yeah. But let me explain why this condition. Let me convince you that it's not a silly condition to have. Okay, so 3 questions then. Is this silly? Asking that I can have an unknot closure. Why do you care? Okay, so why would a 3-manifold topologist care about this? Why unknot closure? Exactly. That's the answer to this. That's the perfect summary, and I'll say a couple more words to elaborate. And then also how to prove it. So I should probably point to that too. Okay, so motivating conjectures. Motivation. All right, these are conjectures that probably everybody here has heard about and knows the history of much better than I do. And it's a long history with a lot of different people contributing, so I'm not going to be able to mention all the results, maybe just some highlights. But here's a popular question, the cosmetic surgery conjecture. Due to Gordon. Okay, so if we're going to be doing Dane surgery along a knot, and what we get is orientation preserving homeomorphic to some other Dane surgery along the same knot, non-trivial knot. Then R was actually R prime. So this is the statement everybody would like to prove. And a second question, which is close to my heart, which I'll maybe have time to come back to at the end of the talk, I hope. And it's another type of cosmetic operation statement, and that's the cosmetic crossing conjecture, also known as the nugatory crossing conjecture. Due to Lin. And this is just the statement that if you change a crossing in a knot, you're going to get a different knot. That's not a very precise way to say it, but any crossing change such that K plus is isotopic to K minus must be at a nugatory crossing. So I'll postpone the discussion of this, its history, and any further progress to later for B, but let's focus on A, because it's relevant to this statement right here, which I don't quite want to erase yet. Well, no, I'll just erase this. Okay. So lots of progress has been made on problem A, though it is still open. Gordon and Lukey's not complement problem implies that R can't be equal to infinity in this situation. There's an obstruction due to Boyer and lines involving an evaluation of the Alexander polynomial. I guess it's the derivative of the Alexander. Oh, thank you. Alexander, the second derivative of the Alexander polynomial valued at -1. Is this sometimes called a Kaplan invariant? Kaplan invariant. So this should not be equal to 0. And then other results include some recent stuff coming from Hagar plurality. So work of Wang, Mi Wu. This is one of 2 different Wangs that I'll mention, and Ojbatsaba. Collectively have results taking advantage of different things from Hagar plurality, like the D invariant, HF reduced, and other pieces of plurality for obstructions. And then kind of following from this, there's a result that I'm going to need to use, and which is kind of the strongest use of Hagar plurality due to Hanselman. So this one I'm going to paraphrase. So if we have our cosmetic surgery, then it must be the case that R is equal to minus R. This part's due to Nianwu. But you know more about R, and it has to fall into one of 2 cases. Either R R is equal to plus or minus 2, or R is equal to plus or minus 1 of those 2. Okay, so you have this pretty strong statement. And there's more content in Hanselman's theorem as well. Like there's information about the thickness bounds and in the plurality, but this is the part that we're going to be using. Okay, so let me restate theorem 1 as theorem 2, which is going to be an equivalent statement. So this is sort of the answer to why ask for an unknot closure and maybe why care. So let's take a strongly invertible knot now. Strongly invertible in S3, okay? Because we're doing surgery in S3, if we have our cosmetic surgery, where H composed with which one do I want to call this one? F. Let's call this homeomorphism F. So where H for this one composed with F is F composed with H, then R is equal to R prime. So it's a cosmetic surgery statement for strongly invertible knots in the 3-sphere. It's a sort of equivariant style cosmetic surgery statement. So our unknot closure means that in the branch that we'll cover, we're doing surgery in S3 as opposed to somewhere else. So unknot closure means doing surgery in S3. Should I draw a picture of a strongly invertible knot and its quotient? Would that be? Yeah. Okay. Let me do that. But it can't be a very complicated one because I'll mess it up. So let's make a strongly invertible knot. Say this. Okay. That'll work. Okay.
Did you need to draw the unknot?
We can just do this. It doesn't matter. The unknot's fine, but you know, just to make it not the unknot, let's do that again. So that's not the unknot anymore. So here is here's my axis, and so what I have here is I have an involution of the 3-sphere. So it takes the 3-sphere to itself. It should, and then it's also going to take the knot to itself as a step. Okay. Now this axis of the involution should intersect the knot in exactly 2 points, which is what we see here. And so the knot, yeah, let me write that down. So K intersect the fixed set of the involution is 2 points. Okay. And the Smith conjecture says that this fixed point set is an unknotted circle. So I'm drawing it as an unknotted circle because it is. Okay, so this is an unknot by Smith conjecture. And I guess this set is what it is by Smith theory. Okay, and so in the quotient under the involution, then I'm going to take a neighborhood around this, and so this picture is going to be sort of floppy, but sort of like this. Just maybe mush down here a little bit. I'm trying to draw this piece down here in the neighborhood around that. Okay, so down here, this is a B3. And then my axis now down here is going to intersect this ball here in 4 points. Here, and then this, sorry, it's very far down, but these are the 4 intersection points. And then this goes through here. It's not intersecting this part of the ball. So this is going to loop back around, and this gives me a properly embedded arc in this ball and another properly embedded arc in this ball. Those are the 2 properly embedded arcs of the tangle I'm considering downstairs. And the point is, and this is using a theorem of Montesinos, is that doing P over Q Dane surgery upstairs is like doing a P over Q slope rational filling of the tangle downstairs. So that's what I'm going to be considering down here is T union my rational tangle. Okay, as a proxy for Dane surgery upstairs. How we're going to prove that is to prove the tangle thing. Sometimes it's the other way around. Maybe you want to prove something about knots, and so you prove something about surgery, but this time it's backwards. Okay, so I want to recall something just as a kind of mini version of the strategy. So we're going to prove, we will prove the first theorem with Commonwealth homology, a version of Commonwealth homology. But as a warm-up, I want to recall something that you can do with the Jones polynomial when you're calculating the Jones polynomial by hand. Here's our Jones polynomial. Normalized Kaufman bracket. So use variable A and write, some polynomial in A with a correction term coming from the rise. And then here's the Kaufman bracket. And as everybody knows, you arrive at this by an axiomatic definition where, where you, take the unknot and assign this to be 1, handle disjoint engines, and by pulling out a factor, deeper diagram here, and by doing this scheme relation, okay, A plus A inverse, okay, very familiar. This is what you do if you're trying to get an expression for the bracket of a link diagram or a link. Okay, but you can also do this for tangles as well. When you do this for tangles, you apply the same axioms, but after doing a bunch of resolutions, you have these crossingless tangles that you don't have turning into closed circles. And so what you end up with instead is an expression associated to t that's I'll write in vector form. So ft is a Laurent polynomial in A as the coefficient of a vector whose basis is going to be with these two crossingless tangles. Right. So this is what you have for a tangle, and then if you want to use a tangle decomposition to calculate the Jones polynomial of the link, so you have your T1 is your T2. Let me just draw the regular numerator closure this time, and you want this to be your link. Then you can pair the two tangle vectors together like this. So tangle like T1 union over conveys your T2. FT1, GT1, 2 by 2 matrix, which you can check on the basis. It should be this. FT2, GT2. Okay, great. All right, this is all a warm up. The observation being that you can pair the tangles together with this bilinear form. Okay, so we're not going to do this. We're going to increase the complexity level and replace cutoff and bracket with some type of quantum homology. But instead of doing this kind of pairing like this, the pairing that we're going to be using is the Lagrangian floor intersection homology as the pairing. Okay. So more about that. Okay, so this is all going to be using theory that was developed by Patelski, Watson, and Zegrovius. And it's not, or I'm not going to use it at all here, but Claudius Zegrovius has a sort of parallel theory for knot homology and tangles that I find to be just wonderful. So, plug for that. Okay, so to this tangle, we are ultimately going to associate two different kinds of invariants, which take the form of sets of immersed curves. So the Barnaton tangle invariant and a reduced, these are like reduced versions, like reduced homology and reduced homology tangle invariant. And they are going to turn out to be decorated sets of immersed curves, but the squiggly arrow stands for like lots of different complicated functors sort of happening, which I'm going to try and say more about. And these are on the four punctures here. They need to live somewhere, and they're on the four punctures here. Okay. Okay, and so the decorations take the form of phi gradings, like what you would want in Kazan homology, homological grading, Q grading, and local systems. Which are matrices. Okay, so more about this now. So this this whole construction of theirs builds really upon work of Barnaton. So I'll add Barnaton's name up here and say something about Barnaton's tangle invariant. Right. Okay, so Barnaton's tangle invariant is denoted bracket T, and then it's sort of mod lowercase l. That L stands for local relations, local groups. Excuse me. And this is defined as an abstract, in a way, chain complex over a cobordism category. This is from Barnaton 2005 paper. So that cobordism category is in endomorphisms, modulo these local relations. Okay. Or a subcategory of this. So what Katelsky and Watson and Zebrovius do is make a correspondence between Barnaton's chain complexes with Barnaton's cobordism category with a path algebra, fancy D. So this is a path algebra over this little quiver. So these are going to be labeled with D, with S. There's some arrows here. Okay, and these are a white dot and a black dot. Modulo the relation that if you go against the flow of the arrow, it should be equal to 0. So D composed with this saddle is 0, and this D composed with that saddle is 0. And the abbreviated way to write this is that DS equals 0 and SD is equal to 0. And if I was being careful, I'd have to put which dot is which here, but when you go against the flow of the arrow. And so a chain complex here, T, this is born here, this Tangle invariant corresponds over here with an invariant called dt. That is is like a type D structure. So there's this correspondence to that's kind of there in the background, and then it's this kind of object that's then translated into an immersed curve. So I guess I need another arrow going somewhere, but I'll just continue on the next board. Okay. So replace chain complex with type D structure and replace type D structure with curve. And a mapping code of 2 of these complexes. This is like a mapping code. Can be translated into immersed curves. So this is roughly like the strategy with the immersed curves for 3 manifolds and porous boundary as well, where you have some sort of type D structure and then translate it into an immersed curve in a rather complicated way. So let me write down these complexes for 2 small tangles that we can look at and calculate with. Okay, so we'll call this, this will be we're going to build a trefoil knot, so let's have a 3 twist, 1, 2, 3 in this tangle. And let's also take a 0 tangle, okay? So this chain complex or type D structure looks like this. And this one is a mapping cone of this with itself and this map H. Okay, and so like this looks like nonsense sort of, but think of this as being like a zero tangle, and S stands for saddle to the infinity tangle. S for saddle, the way you would normally think about it. D stands for dot. So like if I wanted to build SD, and maybe even say that like SD is equal to 0, I could draw a cobordism that shows that that ought to be 0. So, so what D is shorthand for dot, and what that means, this is additional shorthand, but there's starting to be more detail in the picture. You have some sort of component marked with a dot, and the idea is that you're gonna draw a tube from that marked component to your special component, and the special component comes down to parameterizing the four punctured sphere in such a way that like you can make sense out of this correspondence. So you take this and then minus a handle being added, so you would have a tube here minus a handle being added to the special component. So you would have a little handle here. And so this is a formal sum of two literal cobordisms. Right? Because in this cobordism category, you have formal sums of smoothings and cobordisms, and you take complexes over that. So you can, if you wanted to see that like SD is equal to 0, then you can kind of compose this picture. I do want to, it takes a moment to draw, but I do want to draw it here. So if you wanted to check that like the composition of two maps is 0, then you can do that by DS, for example. Going down in this picture, so when I have a dot cobordism, this is special, and here's this tube. It runs from here to here. And then after this, I want to follow it up with a saddle. So at the end, it's going to look like this, and then I have, so just like this. So here's my saddle coming down like that. Okay. And then D is this like tube minus handle. So put the handle here. Saddle part looks the same down here. And then I have a handle. Yeah, great. So these pictures are the same. Like if I hadn't added this saddle here, then I wouldn't be able to slide this handle around and subtract these. But with the saddle there, I can do that. So I can see that this composition is 0. So there's actually like a picture that goes along with this. Okay. But then there's this kind of formal category language, and then it gets sent into some other category, and then sent into yet another category, which is going to be immersed curves of the four punctured sphere. So now let's take this particular complex and this particular complex and draw their immersed curves.
Did you say what H is?
Oh, H is, I did not say what H is. H is another like linear combination of D's and S's. It's like D dot plus D dot plus S, a circle of S plus the other circle of S. And what that is sort of like if you're in this quiver and you like add up all the circles that you can do. Right, okay, so let's draw the immersed curve. This is like a sort of parameterization, a special mark puncture, and for the 3-twist one, we'll have the Barnaton invariant for that one. And then for this one, it's going to be the Homology invariant for this. Okay, and so the red one, color coding them, will be a curve that looks like this. Okay, and the intersection of this immersed curve with this parameterization, that's what corresponds with those two generators over there. And so we should see 1, 2, 3, 4 intersection points for this one. Okay. And it becomes a picture like this. Intersects here, 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 and here. Okay. Great. So there's a few kind of structural observations to make on this with these pictures, which I'll start to list on this board over here. I probably should not have erased those complexes, but oh well. I'm going to point out that these are like we see two different kinds of curves here. There's what's called a compact curve, and that's an immersion of a circle, and it doesn't hit the punctures. And then there's a non-compact curve, and we have this immersion of an interval, and it's going to this puncture. Here's some of the structural results, which is why translating Kavan homology into this picture makes it useful and a useful tool to use. So, and these are due to Kotelski, Watson, and Gropius, the structure of this theory. So, if you do have your Tangle decomposition, as we have for this example over here, so we're in particular looking at two tangles like this, which we can obviously put together as a trefoil knot. Okay, Tangle decomposition. Then the Kavanagh homology of the length that you're after is the Lagrangian homology. You have to mirror one of them. I don't think it matters which one you do, but of the mirror of the immersed curve of Kavanagh invariant of T1 and the Barnaton invariant of T2. And this, I think this is kind of, can be, which one you do Barnaton or Kavanagh doesn't matter. So if we were going to calculate that intersection homology for these two examples, then we would superimpose the blue picture over the red picture and count the intersection of red and blue. So this is Lagrangian intersection homology in S2 minus 4 points. Again. So I'll just put the red over the blue so that we can see it. And oops, that needs to go around the puncture. This is all up to regular homotopy. So these intersect here. Choose different colors of red. These intersect here, here, here. So at least we get the correct rank calculation for the trefoil. Okay. All right. And so we can see, like in the example, that HF of gamma prime is 3. Okay. But there's also a lot of information that's known about the shape of the curves and their combinatorics. So I'll come back to that in the context of a proof sketch, but now I kind of want to sketch out part of the argument for the Tangle statement. So come back to the structure as we need it. So the theorem statement was that if we had this, if you have a tangle with a knot closure, then T union QR is isotopic to T union QR prime, then either T is rational or R is equal to R prime. Okay, so here's a sketch of how that would work. Okay, so suppose let's suppose that we can kind of go back and forth between the three manifold statement. We want to apply Hanselman's result, which is stated for day surgery in S3. So if you did have this, and you did have the corresponding like cosmetic surgery, so if you have this, then R equal to R prime, then Hanselman is going to tell you that you have your two cases. Hanselman implies that either R is equal to plus or minus 2 or R is equal to plus or minus 1 over Q. I'll just kind of do this case because the other case is similar but more technical. So in particular, we also know that the canonic homology of these knots agrees, right? And is bigrated isomorphic, because they're supposed to be the same. We do, so if we take the case where R is equal to plus or minus 2, then we want to use a Tangle decomposition and pick whichever is the easiest one to apply to the plus or minus 2 Tangle filling. And so as it turns out, the non-compact curves are weirder than the compact curves. So we're going to make the non-compact curve the plus or minus 2, since T is arbitrary and T is the mysterious one. Okay. So our Barnaton invariant for the plus 2 tangle and the minus 2 tangle, probably mixing the signs up. Picture plus and minus means that we're going to have a complex that looks like this. DS and SD. The right kind of DS. Okay, and I haven't really said anything about gratings, but one can calculate some gratings and put it in this picture. And so like this grating would be -5, and the grating of this generator would be -4. And then D and S kind of behave differently with respect to the gratings. It doesn't just linearly increase. This one goes up by 2, and this one goes up by 1. So they can all be graded -3, -1. Okay. So T though, what does T look like? It's just some arbitrary set of immersed curves. What does T look like? Well, there's various things that are known about these two invariants. So, if you have a Commonwealth Tangle invariant, Barnaton Tangle invariant, here you can have non-compact, but you have only one of them. You can have one non-compact thing, but then you can have any number of compact components. Whereas on the Commonwealth side, you don't have to mess with this non-compact. You have no non-compact piece, but you do have some possibly large number of compact components. And invariant, you also know that they are classified by properties that you can observe in a picture. In particular, whether they are their type, special or rational. I'll draw something to go along with that, but their type, the slope, the length, and finally by gradings that might be assigned to them. Okay. So just as a kind of generic picture here, like this would be an example of okay, so this is what's called a special curve, and it's special because it encircles the special mark point. The other type is called rational, which that language is sort of borrowed from the Hager-Floor side of this, where the rational curve is literally an embedded curve with a specific rational slope, but we want to have a special and rational distinction here too. So this would be a so-called rational, and it's not special. It doesn't go around the special puncture. So this is like length 1, and it's slope 0. This is length 2. The subscript is the length, and it's slope 0. The length meaning like how many times does it wind around, and the slope meaning, well, if you started with something that was slope 0, like a 0 framed tangle, and you twisted it by an action of PSL2Z, twisted it at the right and underneath, you know, you can make the resulting slope here. These are slope 0. So these curves come in these particular types. It's not just like a crazy squiggle. There's some structure to them. Okay, so with this information in hand, you know what some explicit tangles look like, and now you're going to be considering your pairing. Okay. So you consider that T, this is just a sketch, but you consider that T has an unknot closure. Okay. And from that you can deduce that if you have special curves are going to intersect the unknot closure too much. Okay, unless they are parallel to the curves in T. Okay. And you can also deduce that the rational slopes, unless they are parallel to the unknot closure. This is the special curves of T. And the rationals intersect the rational intersection is okay, but only when the length has to be equal to 1. Okay, so that gives you some information, and so your commoditive doing, you don't know what it looks like, but you can say that it's a collection of specials, some number of them, and together with one rational, and that this has that this is going to have length 1, and that these are going to be slope 0. You can have this information, and then you consider the two pairings that are supposed to give you isotopic knots, the plus and minus 2 pairings. So that means that whatever this sort of collection of curves is, you're going to intersect them with the plus and minus 2, the plus and minus 2 curves. So I don't think I drew them. I'm also getting a little sloppy. I'll draw them next here. So then you pair with plus or minus 2. So one of them looks like this, that, and the other one sort of looks like this, and translated into a curve. Okay. You compare ranks, you make more deductions, you get that the rational is length 1 and slope 0. And you also then have enough information that you can see that the gradings have to have shifted. And then you end up with a grading shift in the special components. Meaning that in your kind of modularized calculation of the Commonwealth, there's some grading shift that happens. And so the cohomology of like the special component gamma I with alpha plus 2 curve is like Q minus 2, quantum homology of the pairing of gamma I with minus 2. And you can't have such a thing, and so that gets you these more isotopic. Okay, so that's sort of some of the kind of flavor of what goes into that. Since I have like just a few more minutes, I'll return to the statement of the cosmetic crossing conjecture, because you can also use this strategy to investigate that kind of problem too. So back to the cosmetic crossing conjecture. So all that we've done so far with this is basically just been able to reprove results that were either proved in writing or known to people, maybe like both type statements. As far as new results towards the cosmetic crossing conjecture, the strategy works, maybe proof of concept, but it's not, hasn't really gotten anything great yet. So the kind of theorems that we can prove or reprove. So a sort of asymptotic version of the cosmetic crossing conjecture, in the sense that we can suppose that T is not horizontally split. Then there exists some integer n such that if you add sufficiently large twists to T, you're going to always be getting something new. So T with the Q1 over 2n tangle is not isotopic to T filled by the Q1 over m 2m tangle for all n not equal to m greater than n. Okay. And this is like probably known to people surely known to people in other ways. So maybe it's just like a book result. And then here's a theorem that's a reproof of something proved by Wang, who also used Common homology, but in a different way than we did.
Sorry, you're saying, is that a knot?
Yeah, this is like K, M, and this is K, and so making this a knot means there's some sort of assumption on T, the connectivity of T should be such that this is not a link when you add to twist to it. So the connectivity has to be.
I think when I said knot, I meant NOT. Are they
Oh,
supposed-
not, yeah,
Yeah,
thank you.
sorry.
They're not isotopic. We just, that would be really weird. And then we can just give a reproof of Wang's result, which is that if T is not horizontally split, but if you put in like the zero closure, it is split, not tangle split, but a link split. So this is a link, and it's a split link, then Kn is not isotopic to Km. All right. I won't write anything else down, but this reproving this involves that we write down a split link detection statement so that we can use the invariant to tell whenever, or split tangle detection whenever the tangle is split or not. That's analogous to something that Claudius and Ty and I wrote down in the Hagar-Fleur side of this, which is also sort of a split tangle detection statement. I think it's a cool technique doing long homology this way, but I'm trying to learn better. So that's what we have. Okay.
Are there any questions